any particular point where you're studying what's happening, say the point that where we're going to focus our attention is right here in this picture, or this one in that picture, there are the three planes that Gauss, who invented all of this, identified, and he named them osculating, rectifying, and normal. And in this picture, which I've redrawn a little bit from yesterday, if you were here yesterday, I'm thinking of my curve coming along like this. So it'd be like this in this picture. And so in here, it's below the osculating plane, as this is, and it's kind of coming through the blue, this thing Gauss called the normal plane, for which the the vector that's normal to it is the unit tangent vector. So imagine that you're just, these planes maybe are made out of paper or something like that, and you're bursting through at this point, and there's the line of sight of the headlights of the little car you're driving on this twisting road, and that's the tangent then to the curve, and it's also the normal to this normal plane. Then off to your left is the normal vector n, which is normal to this plane that Gauss called the rectifying plane, and it points to the center of the circle of curvature, which is in green here, and would have the same curvature that the curve in black has at a given point. The radius of this circle of curvature is what you call the radius of curvature then, of the road at that particular point. And of course that's going to change from point to point in a typical situation. And then finally, the cross product of the t and the n, which are at right angles, is perpendicular to both, and that gives you the normal to the plane in which we are working at this particular point, which Gauss called the osculating plane. And you remember that this means kissing, and his idea is that the circle of curvature is kissing the curve in that it has the same curvature at this point, and is therefore true that they are close together to the one side and the other along this curve when you're reasonably near. So then this same point here is a location where, again, you see the normal pointing in toward the center of this circle of curvature. That would be what you'd call the positive normal. Minus that would also be perpendicular to t, and it would point to the right as I'm holding the stick. If you think of that's left, I do as I'm looking at it anyway. And so we have parallel vectors that point toward the center of the circle of curvature, the unit normal vector, the derivative of the unit tangent vector, which you remember has to be at right angles to the tangent vector because it has constant length. It does not, however, need to be length 1 just because the t is. And we have the component of the vector acceleration that we would represent in the picture here in the darker green that we'd call the normal component. and we have the curvature vector in the brown, and then we have the radius of curvature times the unit normal vector. So there's four vectors there. The darker green, the really dark green, the orange, the pink, I guess there's five really, and the curvature. There are five parallel vectors there. They're all pointing in toward the center of the circle of curvature. And then there are three that are pointed at right angles. The blue is the unit tangent vector, the purple is the velocity vector, and the light green, the pea green maybe is the color, is the tangential component of acceleration. And then the cross product of any of these three with any of these five would give you the normal to the plane, which we call the binormal, and that would be this dark blue. If you do t cross n, since they are unit vectors, this gives you a unit vector. But you could take any of these, like v and the acceleration vector, say v cross a, even though they're not at right angles, they're still going to give you the perpendicular to the plane that they're in. So you could do v cross a over its magnitude, and that would get you the v. You don't have to do t cross n to get the v. If you're using Maple, since it has that command TNB frame, it gives you each of the three. And so if you used Maple to get the t in the n, it would be natural to cross them to get v. But the cross product of two vectors, as long as they're not either one of them the zero vector and they're not parallel like this, that'll get you the normal to the plane of these vectors, even though they're not at right angles and they're not unit vectors. It'll still get you the normal. Which would be then like my meter stick, and then you could divide that by its length to get b, which would be the unit one. So you have choices in the world. Now let's see. These here. If you were here yesterday, or as you can see, I give you the r of t, and it's just go through all these derivatives and get the various vectors like in this picture. As I said yesterday, notice statement 2 there, get ds dt. The r that I've given you to work with, if you do your algebra right, when you do the v, then you do v dot v to get ds dt squared, and that dot product will give you a perfect square. So when you square root that, you won't have a radical. So you're doing something wrong with your algebra if you don't see that the square root of v dot v is no longer needs a radical sign, that you have the square root of a perfect square. And the same is true with v cross a. When you do that, if you dot it with itself, you'll get an expression that you can take the square root of. So, there are two places to look for that. And if you do your algebra right, then this thing will work pretty well. Okay, so keep these pictures in mind as you go through this. And then looking at the 13.5, 13.5 number 1 is over here, the first of the problems, but I have a little bit of discussion before that. This, in this, if you think of your space curve as a track, for example, and you think of a train on the track. So here's a track and a train on it, or here is. You've got your train coming through this direction. And it has a headlight on the engine, as trains do, at least in this country. And in this country, at least, the light's always on if the train is, if the engine's running anyway. And so then you can imagine the normal plane, if you're thinking of a picture like this one. The train is coming through on the track here, and it's just bursting into sight right at this point. So you can think of the curvature then as measuring the rate at which this normal plane, as Gauss named it, is turning. See, as you go from point to point to point along the track, you have new normal plane, rectifying plane, oscillating plane, typically, because you're turning and twisting and so on as you're climbing a hill or something like that. So you can think of the curvature as measuring the rate at which the normal plane turns as the train at the point P. The point P would be there or there in these pictures, moves along the track. So it's the rate per unit length of track then at which the headlight turns from side to side. As you think of the engine and the headlight, and there's curve in the track, so the light turns and so on, and it's uphill or down, so on. Then the torsion, which we're going to learn to calculate today, this is the Greek letter tau, measures the rate at which the engine wants to twist off the track. As if you've ever ridden a train, if you stand up anyway, you can feel the thing kind of, I'm exaggerating a little, but you can certainly feel it. And there is a sense of twist, and at times they do derail, especially when they're hauling oil, it seems. And so anyway, if you have a curve with constant non-zero torsion and also with constant non-zero curvature, it's possible to prove that the curve is a helix. The book says that. They don't do the proof, and I'm not prepared to, but I don't doubt that it's true. Torsion measures then how a curve twists. Curvature, which measures 1 over the radius of curvature for a circle, has curvature the same as the curve if it's this circle of curvature. So the theoretical definition of torsion is this dot product, which we don't really use to do the homework. The computational formula is this 3x3 determinant. Remember, the dots mean time derivative, as Sir Isaac Newton originally invented it. So this is first derivative, second, third. And the denominator is the V cross A magnitude squared. In other words, it's V cross A dot V cross A. Okay, so we have a way then to compute torsion. So Then looking at some of the 13.5 problems, problem 1 wants the vector acceleration so that refers to this picture. Your vector acceleration is what I'm tracing out here, this kind of rose-colored pen. So if you were thinking of curving like this, which is essentially the same as I have in this picture, your velocity would be off this way, your acceleration would be something like that, and then your normal vector pointing to the center of the circle would be something like that. So you see your acceleration then can be written as the sum of two components, the light green and the darker green. So that's what we have here. So if your vector that defines what's happening, the r of t vector, which would be like this one, is constant a cosine, constant a sine, different constant in general b, t, that's a spiral. It's a helix where you're actually climbing, but with constant radius circle. Then your dr dt, doing your derivatives, will give you this, which is your vector velocity. So that's the purple. The magnitude is your speed. You see, if you do the dot product of this vector with itself, you'll get a square sine square plus a square cosine square, and then b square. So then you'll get square root of a square plus b square for your speed. So you're going with constant speed. And then your dv dt, if you go back here, this is the velocity vector. Do the derivative of this and you get minus a cosine, minus a sine, and 0. And this is your acceleration vector. And so then you have the two components here, the tangential acceleration, which would be the light green vector. To get its magnitude, that would be thumb to finger, and as I'm holding my hand up here, you take your formula for speed and you do the derivative with time. This is scalar, you see, derivative. That's a constant, so a sub t is 0. So in this one, if you're going in a spiral with constant speed, then that means you're not speeding up or slowing in your line of sight direction, but you have an acceleration because you're turning, the same as if you drive on the ice in the winter. The car will skid when you're turning, even if you kept the speed perfect, say, on cruise control. So the acceleration then is all normal. So the a sub n, the length of the vector acceleration in this direction, is your magnitude of your acceleration, which would be, back to here, it would be whatever this coefficient is. It would be, in other words, the absolute value of whatever is a. So then what you end up with is that your a sub t is 0, your a sub n is the absolute value of a, and your vector acceleration then is absolute value of a, this a, with the unit vector normal, whatever that vector would be. See, what they wanted you to do, if you read the directions for the problem, for this problem, is to find the a sub t and the a sub n and write the corresponding formula for the acceleration without actually finding t and n themselves by our formulas. So knowing what you do here about the tangential acceleration being the derivative of the speed and the relationships, you can do that. So there's number one. Then I think I went down here. So take a look at problem 6. So this again wants the acceleration in terms of tangential and normal and the unit vectors. This is at a particular point in time, at time 0. And again, they're trying to get you to do this without actually finding the t and the n. And so you have this r of t, and so you do the derivative to get the velocity. Notice it's product rule. You have two variables. So the derivative of e to the t is itself. So you repeat this, and then product rule, you have e to the t, derivative of cosine, which is minus the sine. So because of the product rule, the first component in the velocity becomes two terms. So does the second component. This one, you just have the one variable, so you have root 2 derivative, which is e to the t itself. And so then what you want to do with the common factor like this is factor it out. You can't throw it away, but you can factor it out. So then when you want the speed square, so you have to get the formula for speed in order to do its derivative to get the tangential component a sub t. So doing the dot product of this with itself to get the speed square, you'll have e to the t times e to the t, and then you'll dot this part with itself, which you see is what I'm doing here. So I've written it out so it's not so hard to see then what you're doing. You're taking this times that. So that's FOIL. See, first is cosine square. Outside would be the cosine and minus the sine. And then the inside would be minus the sine and the cosine. So there's two of those. And then last, that'd get you the sine square. So this with that FOIL is these three. Then this one with this one is these three. Then this one with that one is this 2. Okay? And then you see those cancel out, and then the 2 greens make a 1, and the 2 blues make a 1, and there's a 2 there. So there is a 4 in the brackets, e to the t square, and that's your speed square. So there's that. Speed square is here, so square root is 2 and e to the t. So the ds dt comes out as a scalar function. That isn't such a terrible thing to live with. And so your tangential component, like with problem 1, is the time derivative of that. So that's the coefficient of the t vector, so that's the scalar function. But it's still a variable, and you still do calculus. And the derivative then of 2e to the t happens to just be itself. And at t equals 0 then, your value is 2. Then to get to the vector acceleration, you go back to here, or if you prefer to look at it this way, to here, and you do the derivative. Well, say you look at it this way, you have the left-hand function, it's a scalar, but it still is variable, so you still do its derivative. So when you have a scalar function times a vector, and you're doing the derivative, you do the derivative of the scalar function, e to the t, so that's itself, and times the whole vector, which you repeat. Okay, and then you put down the left-hand factor, or the scalar function, this is your product rule, and now you do the derivative of the vector. So cosine is minus the sine is minus the cosine, cosine is minus the sine is the cosine, root 2 derivative is 0. Okay. So then you want to combine, now what you're doing is adding the vectors. So you have the common factor, so it's here, and now what you're doing is adding components. So this component with this one. So you see the cosines strike out, and you have 2 of these. So that's here. That's how I get the minus 2 sine. Now you're taking this component with this one, the sines cross out, and you have 2 cosines. That's in the green. And then root 2 and 0 gives you root 2. So your acceleration, first it's all this mess, you see, but you have to write all this out in order to really see what you're doing. And you've got to do some of this handwritten out, I think, to ever really learn how to do this. This, again, is my endless and bitter complaint with teaching with my math lab, because with my math lab you can game it. You can look at the answer and you can see, but you don't learn it the same way, I'm sure. But if you really write it all down and cross it out, you see this happen. And anyway, then it wants the acceleration at time 0. So e to the 0 is 1, and sine of 0 is 0. So you just get the 2 and the root 2. And then the magnitude of this, if you dot this with itself, you see you get 4 and 2. So that's 6. And that's your squared magnitude, so root 6. So you know that t is at right angles to n. Look at my picture for the last day it's going to be there. And so the a sub t is going to be perpendicular to the a sub n. And again, you see that's in here, it's the dark green component at right angles to the light green component. So what that means is that you, since you're writing your acceleration as the vector sum of vectors that are at right angles, then it also means that if you dotted this with itself, the squared magnitude would be the a sub t squared, t dot t, which is 1, because they're unit vectors. T dot n is 0 because they're at right angles, and then you'd have n dot n, which is 1 because it's a unit vector. So you have squared magnitude is a sub t squared plus a sub n squared. That's on your long sheet of paper that you got when we started the chapter, but it doesn't hurt to remember where we get some of this stuff. So if a sub t is 2, see, we learned that at t equals 0, then you can get a sub n from this relationship. Your squared magnitude, which is 6, is your squared a sub t, which would be 4, plus squared a sub n. So it's going to be the difference. 6 minus 4 is 2. So you can actually get a sub n as a number at time 0. And you notice you've never actually had to compute either t or n as a vector itself, which is the point of their problem. You can get all this without doing that. Okay, now with problems starting with 8, actually I think starting with 7, but 8's the one I've done here. Now it wants the r and the t and the n and the b, and then get their values at time 0. So then you can think of your velocity from here as your derivative, so cosine to minus sine, sine to cosine, t to 1. Acceleration from sine to cosine, cosine to minus sine, 1 to 0. And you note that v dot a is 0 in this problem, if you look at it, because you just simply take these two and dot them. Then you'd have plus sine cosine, minus sine cosine, and 0. Now that's not always true. V is not always at right angles to A for any old problem, but it is true for this one. Okay. And so your speed square is v dot v, which you can get from dotting this with itself, sine square plus cosine square plus 1, so it's 2. So your speed is constant, root 2. See, this thing is tracing out a spiral. I have the handouts, which I should get. Having the vector velocity, you can see that its magnitude is root 2, so then your tangent vector would be this over the magnitude, so it's 1 over root 2 times it, which you can write this way. And this then would be a unit vector that points like V. So you can see that in the picture there. And then the tangent vector at time 0, you have the root 2 over 2, and then sine of 0 is 0, cosine is 1, and so 1 stays 1. And so it's the perpendicular to the normal plane. Again, you can look at my 3 planes there. And then this being constant length, whether it's unit length or not, its derivative has to either be 0 or its derivative has to be at right angles. We've done that proof. Dot something with itself, then you have a constant the dot product, then do the derivative of the dot product, and so that's the vector, the dot, the derivative vector twice equals 0, because the derivative of the constant is 0. So therefore, the vector dot with its derivative is 0, so they're either at right angles or one of them is 0, or both. So this thing is certainly not a 0 vector, because you can see what's there. So it's at right angles. This is not necessarily a unit vector. You'd have to divide by its length to be sure of that. However, what we're working with are these vectors at time 0. So at time 0, your cosine is 1, and now you can see that this, as it stands, is not a unit vector, that its length is √2/2. And you can see that the unit vector that's at right angles here is what you get if you just look at that part, because that's the unit vector. And if you dot this with that, you see you get 0, 0, 0. So the perpendicular to the rectifying plane is this vector, either the -1, 0, 0, or put the number in. Either way, it's the perpendicular to the plane. And this vector, either with or without the √2/2, is the perpendicular to the normal plane at time 0. See, we're thinking of this curve as if this is a picture of it. And here's our picture at time 0. And here are these planes that correspond to the picture, say, at time 0. And there is this normal for this plane, there is this normal for that plane, and there's their cross product as the normal for this plane. See, where this problem's going is it's going to want the equation of the planes. So, continuing then, as I've said, you have a tangent vector which is constant length. Its derivative, which is here, is at right angles, whether this is a unit vector or not. And the actual m that's a unit vector then would be this. And then you can take the cross product at time 0 from the n that you have here and the t that you have back here. Or you could take v cross a over its magnitude to get a unit normal for your osculating plane. So that would be, that would get you that vector, if this is a picture of things at time 0. And so a b then, that's a unit vector, would be here. So at time 0, if you put 0 for t in the original r, it gives you 1, 0, 0. And that's a point at the tip then of the r vector. And that's the point that's in all three planes, the black dot in the pictures. So now we have the rest of the problem. Here's the name of each plane. Here's its normal by letter name. Here's the normal for the problem at time 0. That's a unit normal. This one is a unit normal, and this one is. You just need a normal. It wouldn't matter whether it's a unit normal or not to get the equation of the plane. So you see you have this point that's in the plane, and your general vector in a plane from a point that's given to a point x, y, z is x minus the x coordinate, which is the x minus 1, because there's your point, y minus the y coordinate, which is 0, z minus the z coordinate, which is 0. So then your osculating plane is this vector dot this vector equals 0, and you simplify. The normal plane is this vector dot your general vector, which is the same in all three, equals 0. You get this and simplify. And then your normal plane is n vector dot your same general vector equals 0, and you write that out and simplify. So your answers are y equals z, or anything equivalent to it, y equal minus z, or anything equivalent, like y plus z equals 0, for instance, and then x equal 1. See, x equal a constant in 3 dimensions is a plane where the x is always 1 and y and z can be anything. Just like in 2 dimensions, x equals 1 is a vertical line. X is always 1 and y is anything. So you can have an answer like that would be a plane. So problems 7 and 8 want you to do stuff like this. And then 9 wants you to get torsion. So it's over here. Problems 9 through 16 want you to get B and then the torsion. So here you're climbing in a helix again. And so you get your tangent vector. Well, you get your velocity vector first. 3 cosine minus 3 sine and 4. And then your acceleration vector. So derivative here, and 0. And then from this, you divide by the speed, and you get your tangent vector. As the book says in the directions, problem for problem, like number for number, number 9 in section 13.5 is the same vector as 9 in 13.4, and in 13.4 you were asked to get the t in the end. So their idea is that if you have your answers from that set of work, you can just go there and get them. Well, that may be optimistic, but you got the maple anyway. So you know what to do by now. You get the magnitude of this, and then you divide this by its magnitude, which is the speed, and that gets you this. And you can see that the magnitude here is the 5, because if you dot this with itself, you get 9 cosine square plus 9 sine square, and then 16. And 16 and 9 make 25, and the square root makes 5. So that's where I get the 5 from here. And so this one is that one over 5, right? And then, again, you can take the derivative of this thing, and that'll, since this is a constant length vector, the derivative will be like the pink color in the picture that's at right angles, and then you can divide by its magnitude, and that'll get you to this finally. And you can see that these are at right angles, because if you dot, you have minus sine cosine, and here you have 2 minuses, so plus sine cosine, and then this times 0. So you can see it'll work. Okay, so then you can do your t cross n to get the b. which they want you to do. Or if you preferred, you could simply do this cross that and then divide by the magnitude, which I said. So your V cross A, you need to get the torsion because we're going to calculate with this formula that wants you to divide by V cross A dot V cross A. So it would make just as much sense getting the B to do V cross A over its magnitude. So if you do V cross A, which I didn't write out, this is what you'd get. And then if you dot this with itself, you get 225. So you get 144 out of the 12s, and then 81 out of the 9, and that makes the 225. And you're supposed to know that that is what number square? All of you should know that that's 15 square. Okay, we went to school in different worlds. When I went to school, you had to learn all that stuff. You had to learn the squares up to about 30 by 30 and so on. Well, we didn't have calculators, of course. And so anyhow, to do the torsion, you see, remember the recipe, it's the velocity, that's the first derivatives. The acceleration, that's the second derivatives, the components, and then the derivative of those components would be this one. So that gets me from here, the velocity, see, 3 cosine minus 3 sine and 4. And then the acceleration, minus 3 sine minus 3 cosine and 0. And then the derivative of that, and you see the derivative of sine is cosine. Cosine takes you to minus the sine, so that makes this plus, and 0 takes you to 0. Okay, now you can do your determinant with the basket weave, which is what we've been doing to do cross products. However, you can learn a little bit of algebra here. The original idea about determinants goes back to the French mathematician Laplace, and his way of expanding determinants rather than the basket weave is like this. You can take any column or any row and expand with what are called minors and cofactors of that column or that row. So if you've got a column where everything is 0 except one entry, you can do this. You can say, we'll work with the third column, okay? So you take the entry in the column, that's the 4, and then you times it by what Laplace called the minor, which is what you get if you play crossout. So you cross out the row and the column where the number is that you have here, and then you make a determinant out of what's left. So minus 3 sine, minus 3 cosine, minus 3 cosine, 3 sine. So you keep these in their same relative positions over here. And so your answer in this case will be the 4 times this minor, which you do as a 2 by 2 the way you've learned to do it. So this product minus this product. So you have 4 times the minus 9, which is a factor, then sine square plus cosine square is 1. And then continuing, you would go to the next entry in the row and times by its minor, which is what you'd get if you played cross out with that row, and then this wouldn't be crossed out anymore. So your minor would be this one, this one, this one, and that one. Well, it doesn't matter because you're multiplying by 0, but that's what your minor would be. And then continuing to the bottom, you'd have that, and then playing cross out, you would have crossed out the bottom row, and these 4 would be this minor. The 3 cosine t minus 3 sine t minus 3 sine t minus 3 cosine t. And again, you're multiplying by 0, so you really don't have to do it, but that's what the expansion would be. So you're going to have minus the 4 times 9 then for this, and your b cross a square is the 225, which is 25 times 9, and then the 9's cancel, so this would be your torsion. And torsion can be positive, negative, or 0, and so the sign tells whether you're twisting clockwise or counterclockwise. If you think of the train tipping as you go down the track, you see, you can twist this way, twist that way, okay? So the reason to know that you can do the Laplace expansion, slip there, Laplace transform is differential equations, but that's how you do bigger determinants. The basket weave works for 2 by 2 and 3 by 3. It doesn't work for bigger determinants. So if you have a 4 by 4 or bigger, you have to do something like this. The minors and cofactors, as it's called, works for any size determinant. But you see, it becomes very difficult computationally, because if you had a 5 by 5, these minors are all 4 by 4, and then you'd have to do something like this to cut them down to 3 by 3 and so on. So working with determinants without a computer is hard work if it's a big determinant. But you could do this problem this way, or as a 3 by 3, you can do the basket weave the way you've been doing your cross product. But just thought I'd say something different for a change. And so take a look at problem 24. You're given a line, say, and it has direction numbers A, B, C. So that means the line is like x0 plus AT, y0 plus BT, z0 plus CT. So the direction vector is ABC. So it means that your curve is R of t, you see, is a line graph curve, like that. That the velocity vector, if you do the derivatives, is the direction vector, the L vector for your line, and then these are constants so that you have 0 acceleration. And your speed then would be a constant like that. So then your curvature, V cross A over speed cubed, will be 0 because your acceleration is 0, and when you do a cross product, you have the product of the magnitudes, and that magnitude is 0. So if you're computing torsion, you see your x dot, y dot, z dot would be these numbers, but your double dots in here would all be zero. They're derivatives of constants. And if you have a determinant where any row is zeros or any column is zeros, the determinant is zero. So your computational formula for torsion fails, though, because you'd also be, what you'd really get here, you'd have zeros here, and you have A is zero, so you'd have a 0 over 0. But if you look at your direction vector as ABC for your line, you can get a normal by switching those two and making your third component 0, because try it. You see, if you dot this vector with this one, you get 0. So what that proves then is that all the points on the line lie in a plane for which this is the normal, and that's what you mean by zero torsion. In other words, you can have a line, say like the stick, and you can think of it as in a plane, like the paper. To get my hands in the right place, I can actually do this. Okay. So you can certainly think of your line as the stick, and it has the direction vector ABC. So then there is this, you can associate that with being a line in a plane, like the plane of the paper. Okay, as long as your track stays in one plane, then your train isn't twisting. So that's the zero torsion. So torsion measures how a curve wants to twist from one plane to another, thinking of looking at my points on the curve, and there's the three planes associated with each point. So tau equals 0 means the curve will stay in one plane, which is what we're saying this does. And it's the plane where this would be the normal to the plane, you see. No matter where you are, you always have the same normal. So that's the normal for the plane that the curve is in, so it's in the same plane. That's why I was holding up the paper. Okay, so I guess that's everything. We started here, so. We'll start chapter 14 next week then, and talk about functions of 2 and 3 variables and graphs of surfaces and things like that. So have a good week.